Welcome back to the millimeter wave communication for 6th Gen beyond. So, today we will be covering the lecture number 9. Things that we will be covering are the following. So, now what we will be talking about today is the MIMO FDM parts. In the last class, we have tentatively completed the MIMO beamforming part, and in that context we have also covered what is the first step of finding out the different parameters like equalizers and precoders, but we have not gone to the methods. Method is a separate modules for that, we will be discussing after that, but we just stopped at that point. Why we stopped at that point? Because we wanted to only show you how exactly the complete TX to RX data models are present here. Now, in that context, as we are still in the data model phase, so now we have learned how the MIMO system works there and how in the context of beamforming how MIMO things works. Now, we will be extending this concept to the WebDM part, MIMO WebDM part. So, we already know what is MIMO, and then we are extending it to MIMO WebDM. Okay, so this is the topics, and we will be taking few lectures on the MIMO beamforming, MIMO WebDM beamforming. What are the structural change? Probably it may be a very simple structural change, but overall you should know that. But before I get into the MIMO WebDM part, we have to first know what is WebDM, and I am pretty sure some of you know it, and obviously some of you may be knowing it, MIMO WebDM things, but let us revise that, because WebDM has its own flavor and MIMO WebDM has its own flavor. Probably if you know MIMO WebDM, beamforming would be just maybe just a simple extension to it. Now, let us spend some time on understanding what exactly the WebDM part is, then what exactly the MIMO WebDM part is, and subsequently the beamforming. So, we will be first talking about the WebDM part today. Now, as you say, there is a MIMO WebDM. So, obviously, there is a single antenna WebDM also. So, let us start with that. So, to understand MIMO WebDM beamforming, you have to first understand CISO WebDM beamforming. Okay. So, that is the step by step approach, and once we finish the CISO WebDM beamforming, then it will be just a cakewalk to go for MIMO WebDM beamforming. Okay. Okay. So, let us for the timing just keep aside the beamforming aspect, because first understand CISO WebDM and then we can plug in the beamforming. So, let us assume that I have just a single antenna, physically single antenna in the transmitter side, and I have a physically one antenna at the receiver side, and do not bring the RF and analog chains in this case, we are completely in the baseband model. Okay. So, we are in baseband model. We are completely in baseband. Now, let us say, so what was the channel model from one antenna to another antenna? Does not matter whether it is a millimeter wave or anything, the channel is a FIR filter. So, let us have a FIR filter, let us say H of Z transformation of an FIR filter, right. So, you can always have that, and this is how it is. Okay. And let us say I have the S vector. Now, it is a single antenna, so I cannot have S vector. Let us say Sn will be going there, right, and here I will be taking Rn or Yn. You can say write a Yn also, because consistently we were using the notation Yn. Rn was more of a after the post equalization. So, this is what the data is, right. So, what is the data model that we want to create it here? Let us assume that first. Okay. So, let us say this Hz It is an FIR filter. Let us say it has let us say this is what it is. Let us okay. Now, this is the channel, and we have explained extensively how a channel can be represented as an FIR filter. Now, if I give SN as a data right to this system, this system, what is the yn there, right? So, you can always create yn. Let us say this is my yn. How do I find a yn? If this is the channel, it will be H0 Sn plus H1 S n minus 1 plus H L minus 1 S of n minus L minus 1, right. This is what it is, as simple as that, right. This perfectly fine, right. Okay. Let us say I have yn plus 1, because yn is the first sample. So, I was it was as if like this is my sampling point, somewhere I was sampling my yn, the first one, then yn plus 1, yn plus 2 and so on and so forth. Okay. So, I am just sequentially observing all my data. So, what is yn plus 1? I am only doing few of them. Obviously, this will be n plus 1 minus of L plus 1. So, probably this will be plus 2. I mean, you know how it can be fit into it. So, that is not it. Similarly, I can have as many as data you want, right, straightforward. So, if I stack them together, so that means what does it mean? It means that if I look at my transmission system, I am sending the data one by one, unlike your MIMO, Why? Because in MIMO, I am sending the data at the same time, all the bunch of data I am sending. But as I am using a CSO, single antenna system, I cannot send Sn minus 1 or Sn plus 1 whatever at the same time, right, because I do not have the antenna. So, at a time I am sending only just one, but I am observing one by one. So, I am putting them in memory, okay, and then I am stacking them together. So, that means if I look at here, it is not just one observation, rather I am observing the data in a time, I am observing, not in space, I am observing the data. So, this is my yn, this is yn plus 1, this is yn plus 2 and so on and so forth. So, this is how I am observing it. Now, this is what I am writing it, right. Now, if I stack my data, that means I observe say a certain length of data, I am observing it, it can be m length data or whatever, that means y n minus m minus 1. It will have an equation, I am not writing it, some equation will be there. So, what will I get if I stack them together? So, say I am calling it y bar. This will be what it would be. If you pay little attention, you will see this will be some channel matrix will be coming, right, and some data will be coming, as simple as that. Okay. So, who are they? So, here you can just look at the complete data here. Okay. So, how do I create it? You can say H L minus 1, H L minus 2 dot 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 H 0, it will be all 0, right. Then this will be shifted. HL minus 1, HL minus 2, and then here H1, then H0, some 0. So, at the end it will be H0, HL minus 1 in between, and it will start from 0. This is how the channel matrix is, right. And then take some little effort, you can. So, at some point of time, at this point you may have Sn, and before that you may have Sn minus L minus 1, something like that, and here you can have the data. That is how it is, right. Okay. So, what is the dimension? This should be m cross 1, because that is the number of observation I am having it. Definitely this will be m cross how many? It will be as many as data I want to observe it. So, this should be L plus m kind of thing, m plus, and this should be m plus L cross 1. So, that is the number of kind of data you will observe it. So, in a very simple matrix plus V, I am not writing the V part because that is anyway. So, in a very simple matrix notation, this should be y is equal to, now this whole thing I call it some equivalent H, this will be some vector plus V vector. So, this is how again the data model comes, though it is a single antenna, it is as if like I am creating a multiple antenna. No, it is not a multiple antenna, it is still a single antenna, but it is just that I am observing in time and I am stacking all my observation together. Okay. Now, what is the nature of my H? Okay. You see that the nature of the H is something like a, you are shifting the row to the right side. If you look at if you look at, this is the row, right, and this is one level shifted, right side one level shifted, and so forth, and finally it touches H 0, everything is like shifted. So, what type of matrix this is? This is Toeplitz matrix. So, my H comment is H is a Toeplitz matrix. Toeplitz matrix, that is okay. Maybe the nature, this is how the nature would be, but I am not worried about that. Now, you know how to get back your S. Okay. So, how do you get back your S? You can create some equalizer, because your equation is y is equal to H of S bar plus V bar. So, it is a seesaw model, mind it. It's as if like it is a MIMO. No, it is not a MIMO, just because you are observing at different instance of time. In a MIMO, you are observing at different antenna point. So, that means your observation is at the spatially distributed, but here it is time wise distributed. That means I am observing in different time, but in a MIMO case I am observing in multiple antennas, space wise observation. It is still a seesaw. Now, how do I get back my S? Now, you know how to get back my S. You can always develop some sort of a equalizer, and then you multiply this y, and you know how to develop the equalizer, right. So, let us say if it is an LMMS equalizer, if it is LMMS equalizer, what will happen? How do you develop W? This W would be something like your channel, then R of S, meaning the covariance matrix of the data vector, then it will be H R S H star plus covariance matrix of your noise. This is a simple equation. If it is least square, then your W would be H pseudo inverse, which is nothing but H into whole inverse, something like that. Okay. Yeah, sorry. Yeah. So, many ways you can have some other. So, point is you can develop your equalizer and get back. So, one part of the story. Now, the point is that suppose I would like to do some sort of a pre-coding. Okay. Or rather, I would like to have this question to you: is this equalizer development a simpler task? Actually, if you notice, it is not a very simpler task. What is the problem with this equalizer development? The problem of equalizer development is that this part, inversion creation, this part, inversion creation. Why it is a problem? What if the dimension of y is large? Okay. Let us say I take a dimension of 30 or 40. So, what is the dimension of this inverse? It is 40 cross 40 matrix. So, 40 cross 40 matrix inversion is not an easy task. It will take huge computation. Okay. So, that means I or we, not I, we never want such kind of equalizer development for a large system. For a small system, fine. That is why if it is just a 2 cross 2 MIMO or a 4 cross 4 MIMO or even a 8 cross 8 MIMO, probably this works fine. But even if it is a C-show case, I am observing now if I start making more and more observation, why I need to make more and more observation? I think that should be first answer. Why it is not okay to just have one observation and detect my signal? If you notice, go back here, if you notice, if I just make one observation and try to extract my data, which one I will extract? Just take this, take this data. Now, you have one observation and you have L number of unknown, Sn, Sn minus 1 till Sn minus L minus 1, L unknown, one observation. Can I do it? Can I do a good detection of my Sn? Can I do a good estimation of my Sn? Probably no. So, I have to increase my observation as well. Now, another problem is that even if you increase your observation, this length will start increasing. This length will start increasing. So, you will always have a rank deficient system where you have more and more unknown system compared to your observation. But if you make at least more and more observation, it is better than having just one observation and extracting so many information. That may be a tougher job. So, it is inevitable that you have to make more and more observation from a single antenna case whenever your channel is an FIR filter. Otherwise, its performance will be very poor. And think about it. Suppose L itself is 10, it is a 10 length tap and you are making only one observation. So, you have one observation, 10 unknown data. So, how do you make a decision? Virtually impossible to do that, virtually impossible to detect 10 unknown from just one observation. It's math does not support, mathematics does not support, right, because this will be a rank deficient system. So, you have to make at least some 100 observation, let there be 110 unknown, but at least I can detect 100 better, right, out of the 110. So, that is the whole idea why I need more and more observation here. Now, the problem is that if I want to make more and more observation, now I am stuck in the inversion problem of my equalizer. So, can I do some other thing by which I do not have to face all this equalizer business, I do not have to face it. Okay. So, one such simple technique is that I can have some simple precoder. I am motivating you why how a WebDAM comes into picture. Now, there is a spectrum way of thinking WebDAM, but I am not getting into that. I am thinking from a very simple engineering point of view. Okay. Now, this is one of the issue that I have an inversion problem. So, can I avoid the inversion in my detector and have a very simple kind of detector? I do not want to get into this inversion problem, but looks like it is not possible if the given system is like that. So, what I do is that I develop some sort of a precoder. Okay. So, this is one such technique where you can have a precoder and you can reduce you can actually avoid the inversion in your receiver. Let us see how it can be done. Now, precoder itself is a big topics, let me not get into that, and you can have precoder based on various criteria. Again, let me not get into that, because my intention is not to develop a precoder based on various criteria, rather my intention is to develop a particular precoder, I am repeating that, such that my decoder is of simple enough where there is no inversion. That is my goal. So, let us say I want to have such kind of precoder. So, which means that instead of sending my data vector directly, what I do is that I send it through some sort of a some sort of a peak order. So, let us call it W baseband, because that is the notation we have used it. Let us call it x vector, and that is the one which is serially being transmitted through my transmitter. So, that is what it is. Let's assume that one. So, this is the one which I have developed. Okay. Now, how do I develop? That itself is a very big topics. Okay. I am not getting into that. My here intention is that I want to develop a particular one which will make my decoder life simpler. Okay. So, how do I do that? So, this is my H, and this is where I receive my noise V vector, and that is my Y vector. Again, this is a single antenna system, which means this Y vector is more of a time sample data. Okay. So, what is my data model? Y is equal to H into X, because I am now sending X instead of S, because S will be modified. This is what it is. Okay. Let us put it back, the X part. So, what it would be? WBBT into S bar, because my intention is to get back my S, but still I am not done. It does not solve any problem, because from one problem it just transfer the problem to another, because WBB will also be some sort of a matrix. If it is a matrix, what will happen? H into WBBT is also some matrix, right? Let us call it A matrix, A bar plus B. Does it solve my problem of decoder? No, because it is still I have to do the inversion level of equalizer, right? Because I want to again avoid that. So, I make some trick. Okay. What is that trick? Trick is the following. Now, let us say my channel is known to me, because channel is it is an FIR filter. Let us say I have done a channel estimation, and the channel is known to the receiver as well as to the transmitter. Okay. So, does not matter, let us not worry about transmitter side. Let us say I know the channel, that means this matrix is known to me. Instead of matrix, I would say the channel coefficient H0 to HL minus are known to me. So, I know this H. So, I can develop this whole H. This whole H can be developed, because I know all these coefficients. It is a Toeplitz matrix. I can find out what the H is. That is not a big issue. Okay. So, channel is known to me. So, let us assume channel Hz, that means this all this H0, H1, HL minus 1, they are all known to me. They are all known to me. Okay. So, what is the advantage? So, that means that whole H matrix I know. So, let us do a SVD. So, let us do singular value decomposition. SVD, you know what is SVD, right? So, A is a matrix. I can always break such matrix into 3 component U, sigma, V. Okay. Now, U and V are unitary matrix, and sigma A is a diagonal matrix. It is a diagonal matrix. Depending on the rank of this matrix, you will have, say let us say my rank is R. So, you will have sigma 1 to sigma R component, and there will be 0 the other elements, and rest of them will be 0. So, it is a diagonal element, and U and V are completely unitary matrix. So, it means U star U is equal to U star is equal to I. Similarly, V star V is equal to V star is equal to I. So, that is the property, we have followed it here. Okay. So, similarly here any matrix, and this SVD exists for any matrix, no matter what the dimension, whether it is a square matrix or non-square matrix, it will exist, right. So, let us assume that in my data model, whatever H equal to H matrix, so let us assume it has a SVD. So, let us assume that this H also has an SVD U, sigma H and V star, because if the H is known, knowing SVD is also not impossible. Okay. I am only saying not impossible, does not mean that it is easy. Let us forget about that part, how easy or how difficult it is. Let us assume that I somehow managed to get that. Okay. So, let us assume that part is done, u sigma h v star. Okay. Now, you come back to the data model. So, your y cap is equal to u sigma h v star, and this will be your BBR, BBT. Okay. Now, then you can guess what should be my WBBT. Now, again I am saying WBBT can be found 100 ways or more than 100 ways. Let us not get into that. I am saying I am interested only one particular type of peak order design. Okay. So, let us assume I choose WBBT because it is in your hand. You are the one which is transmitting, right. So, you are the developer and you know all these matrices, because you know the channel, right. So, you assume that you take WBB is equal to V matrix. Note, it is only V matrix. Okay. So, you replace it here. So, that means assume. I should not say assume, I should say take WBBT equal to V. You pick up. Then what will be the data model? It will be u sigma h and V star into V, it becomes I. So, that part is over. Okay. Now, what you do here? Now, you get y cap, right. This is your y cap. Now, what I say? After that, you just multiply it with u. So, you multiply y bar by u star. Let us see what happens. Okay. So, I say let us call it r bar, which is equal to u star into y bar. What will happen? This u will be it will vanish, right. So, this will be sigma h into s bar plus v bar. Let us say that is my new data model. So, what does it mean? It means here whatever I am getting, this is my data model. Instead of this, what I do here is that I multiply this with u star and get my r bar, and here what I do, I pick WBBT which is equal to V matrix. That is the only change I do. I want this type of peak order. Let us see what happens. Okay. That means I pick a peak order which is equal to B equal to u star. So, what will happen? So, finally, I get this one, r bar is equal to sigma h s plus b. Now, let us think about it. What is the decoder strategy? So, now this is the diagonal matrix, right. It is a diagonal matrix. So, what will I do if it is a diagonal matrix? Is it a difficult thing to do? So, it means that if it is a diagonal matrix, I always get individual element of R as whatever some sigma I plus S of this vector's ith element, right, plus this V I. Because it is a diagonal matrix, what does it mean? It means that you have sigma 1, sigma 2 dot dot dot, and there is some S 1, S 2 dot dot dot, and this is my R vector plus V vector. So, if I say the ith element, that means only multiplication of this, and the ith element of this, that is all will come. So, I really do not have to worry about this matrix inversion and all, because I know though it is a matrix, but I am not now dealing with a matrix, because I can individually pick up, and individually the data model will be like this. Can I decode this? Can I decode SI? Very simple. Why? Because this is just like a scalar. Scalar. This is scalar matrix, this is just a scalar value. That means R is equal to sigma into S in plus V. If you know sigma, you can, if you know sigma because you know the channel, and you can get back your S, normal estimation or detection. I do not have to involve any matrix there because just like it. So, this is the beautiful part of a particular precoder. Now, why I am talking all this? Because WebDM, when I talk about that, this is the ramp up, or this is more of a motivation part of why WebDMs come into picture in my life. Okay? Because this simplicity in my decoder is something that we need to worry about. That means, if I can create that particular precoder followed by U star, which is my, I can think of an equalizer, the final equation is just like a diagonal matrix, and I can pick up individual element of my data, and I can, I can estimate my SI, or I can detect my SI very easily. No matrix inversion in this whole process. I haven't involved any matrix inversion. That's one of the easiest thing. Okay, so in the next class, we'll be now moving more towards the what are the issues with this part. Okay, and that gives birth, I would say, to a new concept of WebDM called WebDM. So, this whole thing we just keep it in mind, and we will see that how WebDM can solve some of the issues that even this particular solution gives us. Now, this particular solution, whatever I have talked about, precoder based solution, it only solves the receiver part, because it completely take away the complexity of my receiver design. Receiver is very simple, there is no matrix inversion, but it has its own problem. Okay. So, with this I stop this session, and in the next class I will be talking more about its problem and subsequent, the birth of WebDM concept. So, in conclusion, we have kind of completed the and the reference will be same as what we have. Okay. Thank you.